Hello everyone, my name is Hao Chenjie and come from the Fudan University. Today, I will introduce about image painting and editing with structure prior guidance. First, we will review some works about the image painting with structure guidance. Sketch and edge-based image painting and editing are widely investigated in past few years. For example, EdgeConnect recovers canny edges first and then recovers the colored image with faithful results and better structures. For the editing, such as deep face drawing, can generate high quality faces with sketch guidance through several partial GANs for the face parts. For different face parts. Our main idea is to extend the structural recovery of low-level price for the implanting. Except for the canny edge, we also introduced the wireframe lines, which extracted by the HAWP, a learning-based line detector to enhance the indoor scenes implanting. And our first work, learning a sketch tensor space for image painting of man-made scenes, has been accepted in ICCV 2021. This work focuses in filling the missing creature structures for man-made scenes, which are widely emerged in the real-world application, such as object removal during the travel with many people in the background, and slight artifacts in the regular man-made structure may cause serious discords for the implanting case. Our work has been released. Previous methods mainly suffer from three problems, which are missing creature structures for man-made scenes, unreliable pattern transfer for cropped price. Getting exact prior information from cropped images is difficult, such as edges, lines, and symmetrical segmentations. For example, without the mask augmentation, this module usually outputs poor results. Finally, the implanting module should trade off between good performance and acceptable efficiency. For this work, the motivation is to use the wireframe parser to detect lines with discrete endpoints for the image implanting. This low-level pry can benefit the holistic structures in man-made scenes. Besides, we improve the performance of wireframe detector for masked images and the module efficiency. Our module pipeline can be divided into three steps. First, using the LSM, HAWP, and the canny detector for the line and edge extracting. Then, the pyramid structure subencoder PSS is used to refine the cropped structures to a sketch tensor space. Finally, a decoder, GAN-based decoder, outputs the final implanted image. Unfortunately, HAWP wireframe detector failed to get proper lines from masked image as we mentioned above. We use image masking as a data augmentation to improve the performance called LSM HAWP. And the LSM is simplified from the line segment masking. It not only improves the robustness of masked images, but also achieves better performance in the regular line detection task. As shown in the table, our LSM HAWP outperforms the vanilla HAWP with masked augmentation. During the training phase, we leverage the separability of wireframes to sample lines according to their endpoints, the location of the endpoints, and the mask location. This sampling is more approximate to the outputs from LSM HAWP. We can also utilize it to maintain critical lines in the object removal for protecting the background of man-made scenes. For example, if one of two endpoints is remained, we think that the user tends to remain the whole structure with this line during the object removal. The parameter structure subencoder is consisted with three components. For the partially gated convolutions, we only use gated convolution during the upsampling and downsampling convolution modules, which enjoy competitive results as replace all convolutions to gated ones. But the partially gated convolutions enjoys less trainable parameters and saves the computation. The efficient attention enjoys the advantage of linear attention, which take the key and value production first, then apply the query operation. More details are discussed in our paper. We give some more discussing about the pyramid decomposing separable modules. For the PDS, we learn line and edge embeddings respectively, and combine them with a trade-off attention block to predict colors impacted results for the supervision. To improve the sketch recovery, we optimize the multi-scale structures with two discriminators. It also helps for better decomposing of lines and edges and improve the final impacting results. We test our model in 4 datasets. Shanghai Tech is a dataset with indoor man-made scenes. We also selected 10 classes with most detected lines as man-made palaces 2, and random 10 classes as comprehensive palaces 2. We also tested in York Urban with the model trained by palaces 2. Here are the qualitative results. Our method can get better results in structure recovery in man-made scenes, benefited from the LSM and lines. Our object removal mode can work better with the remained structural lines. And without the remainder lines, our method also outperforms other competitors. Our method can also achieve better edge and line recovery compared with Edge Connector. And we also provide ablation study about our proposed components, while PDS module can learn better structural clues with different sketch resolutions, and the line can help to learn reliable structures in textureless areas for the man-made scenes. And here we remain two problems for our work. The first is, are CNs good enough to tackle the structural recovery? And the second one is, can we extend the edge and the line for the high resolution painting? First, one would ask whether we could module the price with transformers. We review some related works here. The first one is image completion with transformers and called ICT. This module first recovers low-resolution images with bidirectional transformer and uses guided CNN to recover high-resolution details. This paper shows an important conclusion that attention-based transformer with long-range dependency can recover better structures than CNN ones. The next work is resolution-robust large mask imprinting, called LLaMA for high-resolution imprinting with Fourier convolution. The key component is the fast Fourier convolution used in LLaMA, which convert features into frequency fields and learning them in convolutions for the global receptive fields, then converts these features back for the imprinting. LLaMA can recover regular high-resolution details with only the 256 resolution training. So we think these two works should be unified for a better performance. Here is our second work called Incremental Transformer Structure Enhanced Image Imprinting with Masking Positional Encoding, called ZITS in CVPR 2022. ZITS can achieve better results compared with LLaMA, benefited by the high-resolution structure price. We first review some remained challenges during the imprinting. The first is limited receptive fields, and the CNN kernel failed to tackle this large missing. Then the holistic structures recovery in high-resolution imprinting cannot be solved by Fourier convolution from LLaMA. Thirdly, if we introduce new price to the off-the-shelf imprinting modules, it will cost heavy computations to retrain the whole module. Lastly, no positional information is provided in masked regions, which may cause meaningless generation for the center of large masked regions. This motivates our work of incrementally inferring the holistic structural information and positional information to boost the performance of the imprinting. Specifically, we leverage a transformer-based module to tackle holistic structures. Then, such low-level features can be easily upsampled by a simple CNN module. Further, we propose a novel incremental training structure with zero initialized residual addition, called ZeroRA, to incorporate the structural information into a pre-trained imprinting module. Furthermore, we introduce the positional encoding for the masked region, which improves the performance of mask image restoration. Our module pipeline is shown here, which is composed of transformer structure restoration, called TSR, simple structure upsample, called SSU, structure feature encoder, called SFE, and Fourier texture restoration, FTR, from LLaMA, and we will detail each component within it. As for our Fourier CNN texture restoration network, it is mainly consists of several FFC blocks from LLaMA. Our structure feature encoder are used to encode structure into feature maps, then multiplied by the related ZeroRA parameters alpha and added to the FTR. In order to overcome the quadratic complexity of the standard self-attention, Our TSR consists of vanilla attention module and actual attention module, which learns attention maps in row-wise and column-wise to save the computation. Besides, to improve the spatial relation, we also provide relative position encoding for each actual attention module, which improves the structure recovery results. Our TSR enjoys good recovery ability efficiently. To capture holistic structures for high-resolution images, we should upsample the generated edges and lines to target resolution. However, resizing causes zigzag as shown in Fig F to Fig I. But the trend seen for the upsample is also non-trivial because there are ambiguities in the canyon edge from different image sizes as shown in Figure B to Figure C. We cannot use edge to supervise our upsample module. Since lines got from a wireframe parser have good discrete representations without any ambiguities as shown in Figure D and E, with arbitrary resolutions. If the model is trained in lines, it can also achieve smooth, high-resolution edge maps as shown in Figure K. Finally, we design a positional encoding for masked regions. We utilize a 3x3 kernel to extract the distance and direction information relative to unmasked regions, and we encode them into positional encoding, which can improve the results of high-resolution inpainting. Here are the qualitative inpainting results compared with other methods. Our ZITS can obtain clear borderlines. Furthermore, ZITS achieves prominent improvements in the structure recovery compared with Llama. Our TSR can also achieve much better results on both indoor and Palaces 2 compared with our ICCV work. It demonstrates that the transformer-based module is better than in the learning holistic structures for a sparse tensor space, which also benefits the ZITS a lot. Moreover, our zero-RA strategy also improved the convergence and the final performance of our work. Finally, we further provide several high-resolution image inpainting results with our good structural recovery. Then let me introduce some image editing works. Since transformer-based image generation methods have achieved amazing performance in image generation in the past few months, such as image GPT to generate clustered pixels autoregressively, DALL-E can generate images from the input texts, and the timing transformer can synthesize high-quality images with VQGAN and transformer. Here we highlight two important mechanisms in transformer generation. The first one is patchwise autoregressive generation with raster scan, from left to right and top to down. So the autoregressive suffers from limited receptive fields. The second one is the discrete learning as VQVAE and VQGAN. This is our work proposed an image local autoregressive transformer to tackle local image editing in NIPS 2021. As shown in the figure A, our work can solve inconsistent semantics during the editing with the global receptive fields. Moreover, our work can avoid the information leakage for a better detailed editing. Lastly, our ILAT enjoys better generated results compared with bidirectional methods, with powerful local autoregressive generation. In Figure B, we show the differences among bidirectional autoencoder, vanilla autoregressive, and our proposed local autoregressive transformer. Here we first analyze two problems happen in the local editing. The first is inconsistent context. Because of the lister scan of the autoregressive generation, the causal mask can only see previous tokens in attention modules. So, it fails to achieve consistent editing. The second problem is the information leakage. Because of the discrete learning, such as VQVAE and VQGAN, are usually implemented in CNN and attention. So these modules will leak information in masked regions to unmasked ones and crop the editing results. A vanilla solution is to enlarge the editing mask, but this solution will cause results in worse editing results. We propose an image autoregressive transformer for local image synthesis, which enjoys both semantically consistent and realistic generative results. And we propose two-stream convolutions to prevent both convolutions and the transformer from information leakage, thus improving the quality of generated images. We first remove all attention modules in VQGAN and find that it also performs well without attention. Then we propose the two-string convolution for the encoder of VQGAN as TS-VQGAN. For each encoder convolution, we replace cropped features with masked features, and the decoder of VQGAN has nothing to do with the information leakage, so we remain using the standard convolutions and attention in the decoder parts. Then for the transformer learning, we split tokens into global tokens and causal tokens. The global ones enjoy global receptive fields with no information leakage. Only for the generated regions we should generate these tokens autoregressively. As we finish the works mentioned above, the module can be trained with vanilla autoregressive loss. Unmasked features are directly encoded from the encoder, while masked features are replaced with the codebook vectors. Here we show some qualitative results for the post-guided generation. Our method enjoys better results compared with other competitors. For the face editing, timing transformer suffers from the inconsistent result. We also revise timing with our mask strategy in the local autoregressive as timing star. But without the retraining and the two-stream convolutions, it also failed to get proper results. For the ablation studies, our two-stream convolutions can generate better detailed local editing results, which is faithful to the sketch guidance. At last, we will introduce about ICA-SSP work of high-fidelity portrait editing via exploring differentiable guided sketches from the latent space. Our work can get high-quality face editing results with flexible sketch guidance. First, we should introduce about the GAN inversion. As discussed in the image-to-style GAN, we could optimize the latent code of the pre-trained GAN, such as style GAN, for a high-quality generation. We can also get the inverse latent code for a real-world image with suitable optimization strategies. These inverse latent codes can be used to edit for the high-quality results. Our method leverages the gain inversion and repurposes the differentiable classic operator xdog to edit the face. A multi-scale sketch loss is proposed to assist latent code optimization. For the sketch loss, we use maxport to downsample it into 4 different scales for the optimization. We also unify both latent coding and the latent optimization together. We could use the latent encoder to achieve a good latent initialization to reduce the optimization time. That's all. Thanks for the listening of my introduction.